Today, scientists accepted the kinetic molecular theory as valid theory. The following are its features. All matter is made of atoms and may join to form molecules. Atoms and molecules are in constant state of motion. Atoms and molecules event forces that are electrical in nature. In liquid, atoms and molecules move quickly and can change position while joined together. In gas, the atoms and molecules move quickly and bend to move in all directions. The last one is the sum of potential and kinetic energies of molecules in a state of motion is the total thermal energy of a substance. So, I will tackle to you what is the temperature. The temperature is the hottest or coldness of a substance is a measure of its temperature. When a substance is hot, it has a higher kinetic energy than when it's cold. Hence, the average kinetic energy of the atoms and molecules in a substance is a measure of temperature. So, the instrument used to measure temperature is called a thermometer. So, this thing is very familiar to us. So, this thing is the thermometer. In a thermometer, a liquid such as alcohol in a hollow glass tube expands when heated. A scale is attached to the glass tube from which temperatures are read. Other thermometers use bimetallic strips that are made from two types of metals. The strips consist of two different metals. So, that expand at different rates as they are heated. So, they are usually made from steel and copper, or in some cases, steel and brass. So as the temperature changes, the two metals in the bimetallic strip expand or contract. The larger the bend, the greater the temperature is. So Celsius scale or centigrade scale is the numerical scale used in thermometers from which temperature is being measured. An example is the temperature of the freezing and boiling point of water. The illustration above distinguishes the Celsius and Kelvin scale readings, which can be expressed in an equation such as Kelvin is equal to degrees Celsius plus 273. So that's all. Thank you.
Good morning, everyone. My name is Sean Darcy, and today I will be discussing to you about linear and volume expansion.
If an object expands when heated, the change in length, linear expansion of the object provides a measure of expansion. Linear expansion and volume expansion are both type of thermal expansions, which is the change of size of an object due to heat.
So for example, we have this, yung object. Tapos tinaasan natin yung temperatura, yung object na yun nag-expand. Tapos pag binabaan naman natin yung temperatura, kumbaga yung object is lumiliit. For example, we have this bar. Length. Which is yung length. So what will happen, as kagaya nga nung sabi ko kanina, pag binasa natin yung temperature niya, yung bar nag-expand by the amount called delta L or delta L. So, if tinasa natin yung delta L, yung size ng bar is parang nag-i-expand. Pero pag binawasan naman natin yung temperatura, yung bar nagiging kumbaga lumiliit. So, the expansion of the object is the change in length, which is the delta L, and is directly proportional to the increased temperature or the change in temperature, which is the delta temperature. So when two proportionalities are combined, a constant A is added to the equation, which it can be written as delta length or delta L equals A multiplied by L naught and multiplied by delta temperature or delta T.
Where delta length is the change in length in meter. A is the coefficient of linear expansion in degrees Celsius -1. L naught is the original length in meter. Delta temperature is the temperature change in degrees Celsius. The table shows value of coefficient of expansion of different objects.
The importance of thermal expansion in engineering. Architects and engineers design and create a structure that allows the thermal expansion of materials that will be used. Ignoring their thermal expansion may place the structures in danger of collapsing. So, the passage begins by highlighting the crucial role of architects and engineers in designing structures that account for thermal expansion. Ignoring this phenomenon can lead to structural damage or collapse. Emphasizing the practical significance of understanding and incorporating thermal expansion principles into design. Later, I'll be discussing the provided formulas and examples to illustrate how to calculate the change in length or volume due to temperature changes. So, the relationship of the volume expansion is expressed mathematically as delta V is equals to beta V delta T, where delta V represents the change in volume. Beta represents the coefficient of volume expansion in per degree Celsius to the power of -1. V0 is the original volume in cubic meter. Delta T represents the temperature change in degrees Celsius. This formula is fundamental to predicting and managing volume changes in various materials due to temperature fluctuations. So, I have here the sample problems in applying the volume expansion formula. So, number 1. A steel beam used in the construction of a bridge is 9.2 meter long at 20 degrees Celsius on a hot summer day. The temperature increases to 40 degrees Celsius. What is the change in length due to linear expansion? So, this problem focuses on linear expansion or change in length, which is a special case of volume expansion for objects with one dominant dimension. We're going to use the linear expansion formula to demonstrate on how to calculate the change in length given the initial length coefficient of linear expansion and temperature change. So the original length of the steel beam is 9.2 meter. The final temperature is 40 degrees Celsius. Then the given initial temperature is 20 degrees Celsius. And this is the given coefficient of linear expansion for steel. Note, the value alpha equals 1.2 times 10 to the power of -5 per degree Celsius is not derived within the solution. It's given as known constant. These values represents the coefficient of linear thermal expansion for the specific material of the steel beam. The next thing to do is to calculate the temperature change. Delta T equals T2 minus T1, which equals 40 degrees Celsius minus 20 degrees Celsius, which equals 20 degrees Celsius. Next is substitute values into the formula. Delta L equals 9.2 meters multiplied by 1.2 times 10 to the power of -5 per degree Celsius, multiplied by 20 degrees Celsius. So the last thing to do is to calculate the change in length. So this is the final answer. The beam expands by 2.2 millimeters. So I have here another example. A gasoline tank in a car has the capacity of 60 liter and 20 degrees Celsius. If the tank is fully filled without a cover, how much gasoline will overflow if the car is left in the sun and the gasoline reaches the temperature of 45 degrees Celsius? So the problem directly applies the volume expansion formula to calculate how much gasoline will overflow from a tank when the temperature increases. So our solution will steps clearly show the substitution of values into the formula and the calculation of the resulting volume change. The original volume of the gasoline is 60 liter. The final is 40 degrees Celsius. And the given initial temperature is 20 degrees Celsius. And then this is the given coefficient of volume expansion for gasoline. Now we need to calculate the temperature change. Next is to substitute the values into the formula. After that, calculate the change in volume. So this is the final answer. 1.4 liters of gasoline were overflow. So the excerpt underscores the importance of understanding and accounting for thermal expansion in various engineering applications. The provided examples demonstrate how the volume expansion formula can be used to predict and mitigate potential problems associated with temperature-induced volume changes and structurals in systems. This knowledge is essential for ensuring the safety, stability, and longevity of engineered structures. Thank you for your time and attention. I hope this report has provided you with valuable insights.
Let's move on to the next topic, which is heat and the first law of thermodynamics, which is also called the law of conservation of energy. With focus on a specific heat capacity, this report will explain what heat is, how it's transferred, and the implication of the first law of thermodynamics. It then delves into a specific heat capacity, defining it and stressing its significance through a comparison of various materials using a bar graph. Let's have first heat. So what is heat? So heat is the kinetic energy of the water molecules increases as the temperature rises. It, for example, an electronic stove heats up a metal container with water. The thermal energy that flows from one object to another due to a difference in their temperature is called heat. So it means heat is the transfer of thermal energy between objects at different temperatures. And the first law of thermodynamics, which is also called the law of conservation of energy. It was proposed in 1847 by James Joule, where it states the change in the internal energy and the work done by a body in its surroundings is equal to the heat energy absorbed by the body. So, the first law of thermodynamics, it states that the change in a body's internal energy plus the work it does equals the heat absorbed. And thermal properties of different substances vary because they are made of different atoms and molecules. The quantity of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius is called the specific heat capacity, and the unit is joules per kilogram degree Celsius. There are various of specific heat capacities of various materials. As shown in the tables, it provides specific heat capacities for various substances measured in joules per kilogram per degree Celsius. This value represents the amount of heat energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. The table shows that different substances have different specific heat capacities. For example, water has a significantly higher specific heat capacity than many other substances. The values provided are average values. the inclusion of water in its three phases, which is the liquid, ice, and steam, highlights how phase changes drastically affect specific heat capacity, and values in most cases must be regarded as average values. And now we can summarize the relationship between heat and specific heat capacity, as the formula E sub h is equal to mc, or temperature change, whereas we can calculate the A sub h, which means it is the heat energy gained or lost in joule, while the m stands for the mass in kilogram, and delta T is the temperature change in degrees Celsius, while the C is the specific heat capacity in joule per kilogram degrees Celsius. By knowing any three of these values, we can calculate the fourth using this formula. The tables provide the necessary C, which means the Celsius, values for various substances, enabling you to perform these calculations. In essence, these tables and the formula provide a practical tool for understanding and quantifying heat energy transfer rather. All for my part. Thank you.
Good day everyone. Today we are going to solve this sample problem. The problem is calculate the heat needed to heat up a 2.0 kilograms of copper from 30 degrees Celsius to 80 degrees Celsius. So this is the formula for this problem. The mass is 2.0 and this the T2, which is on 80 degrees Celsius, minus 2 T1, which is 30 degrees Celsius, is equals to 50 degrees Celsius. And next is the C, which is 3.9 times 10 squared. And this one another is 0 kg. This is the formula. Heat, which is heat energy equals to M mass C specific heat capacity, and it is the temperature change. The mass is 2.0 kilogram and the C is 3.9 times 10 squared. The kilogram minus degrees Celsius and 50 degrees Celsius. The final answer is 3.9 times 10 raised to the power 4 joule. And this is the final answer of this problem. This is the second problem. How much heat is lost if 54 grams of iron is cooled from 90 degrees Celsius to 10 degrees Celsius? So, this is the formula again. The mass is 54 grams. 54 grams is equals to 0.054 kilogram, and the temperature too is the 10 degrees Celsius, and the temperature one is 90 degrees Celsius is equal to negative 80 degrees Celsius. The C, is 4.5 times 10 squared joule kilogram minus degree Celsius. This is AH equals to MC and T. The M is 0.054 kilogram and the C is 4.5 times 10 squared G dash E kilogram and negative degrees Celsius and negative 80 degrees Celsius. Imo daw sila i-times and the answer is negative 1.9 times 10 cubed G. And this is the final answer in this problem. And that's all.
Good morning, everyone. Today we're going to tackle about the law of conservation of energy. Now, what is law of conservation of energy? Law of conservation of energy is a warmer substance loses heat to a colder substance when the two substances are mixed using the law of conservation of energy. We have heat loss is equal to heat gained. We have symbols of E, heat lost is equal to E, heat gained. The, the meaning of E is energy. That's why the symbols of E. I mean the unit. The sample problem illustrates this kind of concept. We have the sample problem number 1. Now, determine the amount of water needed with an initial temperature of 100 degrees Celsius that must be added to 1.0 kilogram of water with a temperature of 10 degrees Celsius to have a final temperature of 37 degrees Celsius. We have here a given, which is the warm water and the cold water. The warm water cold as heat loss, as the cold water is called heat gain. Now the warm water we have the MW, which is the mass we are going to find, and the C, which is the capacity. C is equals to 4.2 times 10 to the power of 3 joule slash kilogram dash degrees Celsius. And we also have the delta, which is in time. Delta T W is equal to T final minus T initial is equal to 37 degrees Celsius minus 100 degrees Celsius is equal to negative 63 degrees Celsius. That is the delta. For the cold water, we have the MC, our mass is 1 kilogram, and for the capacity is 4.2 times 10 to the power of 3 joule slash kg dash degrees Celsius, which is the same as the warm water. Also, we have the delta T C equals to T final minus T initial is equal to 37 degrees Celsius minus 10 degrees Celsius is equal to 27 degrees Celsius. We have here the solution. Heat loss by warm water is equal to heat gain by cold water. We have minus M, our mass, W, dot plus C plus delta T, our time, W is equal to MC plus C plus delta time, delta T, C. Substitute values are minus M is our mass. As for our capacity is 4.2 times 10 to the power of 3. For our total time is negative 63. For the other side is equal to our mass is 1.0, and for its capacity is still same 4.2 times 10 to the power of 3, but difference with a delta of 27 degree. Now we have to simplify by, using our mw as our mass is equal to 200,064,600. That's when you simplify these two numbers or variables. Now, as for the other side, we have 100,013 113,400. We have here that 1.0 times 4.2 times 10 to the power of 3. That's equal of 113,400. To solve for mw as our mass, here is the solution. mw is equal to 113 degrees. 113,400 and 264,600 is equal to 0.40 0.428 kilogram or 0.43 kilogram. For sample problem number 2, a brass object of 1 kilogram mass has an initial temperature of 88 degrees Celsius and is submerged in 0.44 kilogram of water at 6 degrees Celsius. The final temperature is 20 degrees Celsius. We have to find the specific heat capacity of the brass. We have a given brass and water. Same given from the sample problem number 1, but different given from sample problem number 2. We have brass and water. Same here, we have mass, our delta, and our capacity. Our mass is 1 kilogram, and our delta is 20 degrees Celsius minus 88 degrees Celsius is equal to 68 minus 68 degrees Celsius. As for our capacity is still unknown. To find water, we have mass is 0.44 kilogram, and for our delta, we have the 20 degrees Celsius minus 6 degrees Celsius is equal to 14 degrees Celsius. As for the capacity, we have the 2.2 times 10 degree to the power of 3 Joule slash kg dot dash degrees Celsius. We have a solution here for sample number 2. Solution is we have the EH loss, which is the energy heat lost, is equal to energy heat gain. We have minus M B CB delta B is equal to MW CW and delta TW. We have minus 1.0 kilogram, and our capacity is still unknown, and our delta is negative 68 degrees Celsius is equal to 0.44 kilogram times 4.2 times 10 to the power of 3 Joule slash kg dash degrees Celsius times 14 degrees Celsius. Now to simplify, we have the capacity 68 is equal to 25,872, and we multiply this and we get the capacity is equal to 380.747 is equal to 3.8 times 10 to the power of 2 Joule slash kilogram minus degree Celsius. And that's all for this video. Thank you for watching of Law of Conservation of Energy. I am Lafron Sigosela, and the next reporter will be Ray Villegas.
So, hello everyone, I'm Nikinha, and we will talk about latent heat. So, what is latent heat? Latent heat, also known as latent energy or heat of transformation, is energy released or absorbed by a body or a thermodynamic system during a constant temperature process, usually a first-order phase transition like a melting or condensation. Latent heat can be understood as hidden energy, which is supplied or extracted to change the state of a substance without changing its temperature or pressures. There are four types of latent heat. Latent heat of fusions, latent heat of vaporization, latent heat of sublimation, and the last is latent of condensation. So, in latent heat of fusions is the heat absorbed when solid turns into a liquid, and the latent heat of vaporization is the heat absorbed when liquid turns into a vapor, and latent heat number 3 is sublimation, the heat absorbed when a solid turns directly into a vapor. And the last is the latent heat of condensation, is the heat released when a gas turns into a liquid. So, during the phase change, the energy is used to break the bonds between particles, so there is no increase in the kinetic energy of the particles and no rise in temperature. For example, a cup of soda and ice will remain 0 Celsius until all of the ice has melted. So this graph shows that the temperature versus times graph of water. The temperature of water increased from negative 20 Celsius to 120 Celsius and produce a system in 7.5 minutes. So, ang inikibay na set, amoy nga temperature or Celsius kibali. Then, diri nga to makita ang 0 to 120 kibali. Then, wala sa diri sa ubos, amo ini ang time kibali or minutes. So, ini na part diri, joy diri nakakuan na solid or ice. Walang sa diri is nabilong ang liquid, water. So, ang sa diri sub na area, diri makita ang melting of ice. So, nabilang na sub diri na area ang boiling of water. Whereas sa diri, amo na ini atong makita na to na sa steam kibali siya atong vapor diri lang siya. Kung pag bilong sa diri gapon ang gas. Amo jo ay solid, liquid, and gas. So,
amo kay bali atong kuan kay amo man kay bali ini atong 100 ay negative 20 Celsius to 120 Celsius. So amo na ini ibali sila. So the heat involves in change in state is called dilating. That is, the heat involves in a change in state is called the heat. That is, E L equals in L. So where EL is the heat transferred in Joule Kibali. So, amo ini sila ang EL is the responding. While ang M, ang ini Kibali sila is amo ini nag into in yun. While ang M, amo kibali ini ang tagtawag na mass. Mass in kilogram kibali ini siya. While ang L, amo na sa gapon siya like per kilogram na kibali siya. So, the latent heat of fusions is the amount of heat necessary to melt 1 kilogram of a substance to form a liquid, or the amount of heat given off from a 1 kilogram liquid that changed to solid. So, the latent heat of fusions is the amount of heat required to melt 1 kilogram of substance to form a liquid at a constant pressure and at the substance melting point. So, the opposite of latent heat of fusions is the heat of solidification, which is the amount of energy required to turn a liquid into required to turn a liquid into a solid. The heat of solidification has the same magnitude as the latent heat of fusion, but the opposite sign. So, that's all, and the next reporter will give an example and also the solving about this latent heat topic.
Hi, good day everyone. My name is Geraldine Siscovia and now I am going to tackle the latent heat of vaporization. The latent heat of vaporization is the amount of heat necessary to change of 1 kilogram liquid to 1 kilogram liquid vapor. So, from the word amount of heat, kibali kung pila ang ija kapasoon para ma-change ng 1 kilogram liquid to 1 kilogram liquid vapor. So, para mas masabtan, ijura kang tanawon sa diri na table para mas makasunod ka mo sa nan makagets kung tag-uno pag-answer. So, here's the example. But before that, we need to use this formula to get the answer. And here's the problem. How much heat is required to change 2.0 kilogram of ice to water at 0 degrees Celsius? So our solution, we need to multiply first the 2.0 times 3.3. So the answer is 6.6. So we need to copy the 10 to the power of 5 joules. Makita ato sa table kung naidapit ang 3.3. Then our final answer is 6.6 times 10 to the power of 5 joules. So that's all everyone. I hope you all understand and please feel free to ask any further questions. Thank you.